Good evening, everyone. So, myself, Anchal Singh. I am a PhD student at ISC Bangalore, and I am your TA for this course, taught by Professor Bhim Singh online at NPTEL platform. So, today is the seventh session of our tutorial, and this session will be dedicated to the design of passive power filters. So, before starting, if you have any doubts, you can please let me know. Venkata sir, you were having some doubt. Can you please unmute yourself and tell me?
Yes, madam. Last assignment I have some uh, doubts, madam.
Last assignment that was based on the topic.
Last 1 minute, madam. Week 7. Madam, in the recently one option is given, madam. Solution 2023 solutions. 2020. In that given answers differ from which is given in the actually that assignment 6, madam.
Uh,
Both are different, madam.
Regarding that, you will have to mention in the discussion forum, as I have mentioned
Yes,
before
madam.
also.
I already mentioned, madam, but no response from that, madam.
You can wait. They have like some hours given to them to respond to those discussion forum queries. They will definitely respond back.
In week 7 assignments, I have two problems got one answer, madam, but they are given different answers. For that, I need some clarification, madam.
Okay, okay.
In
So
week
you can
7.
wait for their reply. I'm sure they will get back to you regarding that reply. And
I need a solution for that, madam. They are given one solution, but I had one answer for that. But they are given another answer. That is the different from other another. This is another assignment, madam. This is a week 7 assignment.
okay, can
In
you
that problem number 8 and 9, madam.
Okay,
Can you
can you mail this query to me exactly what is the problem and what is given in the solution and what exactly do you want? Okay,
madam? It is simple problem, madam. I will read once, madam.
Sir, this is actually I have a fixed time and I have to complete. So I have two
Okay,
big
okay.
problems to be solved today. So otherwise we'll not be able to complete on time if we discuss. And I only have one screen which I use for recording. So I cannot go back and look at the previous assignment also. That is why I'd ask you to send me a mail beforehand so that I can prepare for the queries before the session.
Okay, okay, madam.
Okay,
Okay,
so you write these problems on the discussion forum because they are a different group of TAs who are preparing these solutions and questions. So, in order to make any changes there, even if you discuss it with me, I will not be able to make any change there. That is actually the issue.
not make change, madam. My confirmation with confidently I have to say, madam. That's why I am getting the one answer, but they are written another answer.
So, they
Uh,
might have given the solution for that as well, right?
Given, madam, but active component they are given IS1A in that question asked, madam. For that they will given IS1 into tan pi. But I have written the formula IS1 active is equal to IS1 into cos phi. But
Okay,
why they are written tan pi? I don't know, madam. How they are writing like that? That's why I'm asking, madam.
okay. That might, so even the value is different, you are saying.
Value is different, madam. But overall, fundamental component is same, madam.
Yeah,
But
yeah, yeah.
active reactive components are differs, madam. Both of the from me it differs that solution, madam.
Okay, okay. So you can once, I think this is a pretty straightforward thing. You can write it down in the discussion forum and also you can mail it to me so that parallelly we can also discuss it in the class. Okay.
Okay, okay, madam.
Okay.
Okay.
Anybody else has any queries? Okay, so we'll start today's session. So far we have been discussing about, we started with power quality. What are the needs? What is the need for working on this topic? Why make a separate subject called power quality? Then we saw that there are a lot of problems due to the nature of load that is changing. Initially, the nature of load was pretty much straightforward, and the curve or the waveform of the load current was pretty much sinusoidal in nature. But with the advent of new kind of technologies, what is happening is the nature of load is varying, and because of that, what is happening is there are a lot of power quality problems that are coming into both the current and voltage. So from there, we realize that because of the new kind of load, new kind of problems are coming up, and we'll have to deal with it. So before dealing with it, we classify these current power quality problems and voltage power quality problems, and then based on that classification, we started finding ways to solve this problem, solution to this problem. And in order to find solution to this problem, in order to tackle current power quality problems, we discussed D-STATCOM. And for voltage power quality problem, we started with discussing about DVR, that is dynamic voltage restorer. And then we discussed about UPQC, which is a hybrid of both D-STATCOM and DVR, which takes care of both current and voltage power quality problems. And before these are all active type of devices. Before that, we discussed about passive devices. The difference between passive and active devices is the presence of switching element. Passive devices only have RL and C components, whereas active component has R and C components along with switches. And due to the presence of the switches, we are able to get variable compensation. Whereas in passive compensators, we were able to get only fixed kind of compensation. Okay, so that is the change that we are getting. But because of the presence of switches, what is happening as a con here is our circuit is getting a bit complicated compared to a simple passive filters. So from passive compensators, we started discussing active compensators. Then after UPQC, in the last week, we were discussing about the non-linearities in the load. We talked a lot about what is the waveform of the current kind of load, what are the actual problems, what are the harmonics present in the load, and what kind of loads are nonlinear in nature, which are present in our surroundings. So this was our topic for last week. Now, after discussing the lot of problems and nonlinearities in the load, what we will be discussing this week is passive power filters. So as the name suggests, since the word passive is coming into picture, we know that it will be using RL and C components, that no switches will be present. Switches will not be present in this compensator. And the main purpose of giving it a whole new name is that the main purpose of these designing these passive power filters was to take care of harmonics and power factor. So these passive filters are designed specifically to take care of a particular harmonic. It could either be third harmonic or fifth harmonic or seventh harmonic. Any harmonic could be whichever is creating a problem in our system. First is, suppose this is my system. This is my electrical system. Okay. So what I'll do is it is consuming certain current IL. This is my system and this is my source. So first step will be to observe what is the nature of this IL, what kind of power quality problems are present in this IL. Suppose I take this waveform of IL, I do a FFT, that is fast Fourier transform. Why would I do that? So that I can observe the various frequency components that are present in this current IL. So based on the FFT of this current waveform IL, I'll be able to obtain what all harmonics are present in this waveform and what are the magnitudes of the harmonics. Suppose my fundamental component, third harmonic and fifth harmonic are present. Fundamental component is 70% of the waveform, then third harmonic is 20% and fifth harmonic is 10%. Let us just assume this, okay? So now I know that third harmonic is the most dominant harmonic in this system. So depending on what my system is, if I am using this system is a medical equipment, then I will take care of both third and fifth harmonic. So I will put passive filters, so which will compensate both third harmonic and fifth harmonic. But if my system is a simple, toy, let us say it is a toy, then I might not even compensate the third harmonic also. I will just let this equipment sit there until unless there are government-based regulations which are being imposed on the nature of this IL. And the if government is saying that I government regulations say that I cannot consume 20% of third harmonic current, then I'll have to reduce it. So either it's mandated by the government or it is a requirement of the system. So they based on your application, you will have to figure out what kind of compensation or what kind of filter you want to design. So now in today's lecture, we will be discussing about the design of passive power filters. Okay, so far we have been discussing that there are a lot of power quality problems, and which result because of those power quality problems, there is increase in RMS supply current. Because of the increased RMS supply current, there are a lot of losses. Because of the losses, the power factor reduces, and because of these losses, we are unable to utilize our existing infrastructure to its full capacity. We have to derate our system. We studied about derating, right? This derating of distribution system. And because of the losses, heating takes place in the system, especially in electrical machines. And because of that heating, what happens? If you do the reliability study of these equipments which are connected to the power supply, you will realize that if I'm giving ideal power supply to any equipment, it then if it is work able to work for 10 years compared to the situation when I am giving it fluctuating kind of power supply or power supply with power quality problems, then the life of that equipment might reduce to 5 years or 7 years. So that the life of the equipment is impacted. But since it happens over a long interval of time, we don't realize that what is the cause of my equipment getting damaged. We think that it's normal, but it's actually the cause of the power that we are receiving. So because of those problems, distortion happens in voltage waveform. And then there is because of the high frequency components which are present in due to the harmonics, interference occurs in the communications line, which are running
Madam,
parallel to our system. Yes, sir.
uh, that compensating device passive also RLC elements, madam. These filters also RLC elements. What is the both work difference from both of them, madam?
So initially the filters that we studied, if you might have remembered, we were using them for balancing the system, right? We designed those
Okay, madam.
passive filters in order to so they are still RLC elements or combination of RLC elements, but the goal here has changed. There the goal was to balance the system. Here the goal is to compensate the harmonics. So we will be just mainly focusing on harmonics and power factor correction using these filters.
By using the that compensate device, you can't eliminate that harmonics, madam. Or
You can they are basically the same thing, but that time when we were discussing those kind of passive filters, we didn't focus on the harmonic based, right? We just focused on we considered that the system is not we never talked about harmonic so far, right?
yes,
So,
madam.
so we are introducing that if we take everything at one time, it is difficult to learn. That is why when we are learning anything for the first time, we take one problem at a time. So that time we use those compensators in order to balance the system and for power
Okay, that
factor
is
correction.
generalized one. This is a different
Yeah,
harmonics power factor like separately or discussing.
yeah. But in actual practice, what will happen is if your system has power quality problems or harmonics, all these things, all these tools will be used parallelly. Okay, they won't be separate there. Here we do separate discussions only for the sake of understanding them clearly so that we don't get confused from the start.
Okay, madam.
Okay. So when we talk about traditional passive power filters, there are active shunt filters. Okay, so the solutions are they will start from similar to what we have been studying so far about the filters in general. So they are also categorized into the same way like passive power filters which we are studying today, and then we'll go to active shunt filter, active series filters, and hybrid power filters. The same thing that we have been doing so far. And when we talk about power filters, then they are again categorized into passive, active, and hybrid filters. Hybrid is basically again a combination of both passive and active elements. So when we talk about passive filters, all of these can be categorized into shunt and series. And when you talk about hybrid filters, so hybrid filter is basically a combination of both passive and active. So if I am saying that the first a hybrid is equals to passive filter plus active filter, then Then the first filter that I am using in my system, if suppose this is my configuration, let us assume that this is the topology of hybrid filter. If this is my first filter and this is my second filter, if my first and second filter both are passive, then I can call it passive passive. If my first is active and second is passive, I might call it active passive. And if my first is active and second is also active, then I might call it active active. So we could use that in any particular combination. This active active we have seen, right? The UPQC that we have studied, that comes under this category because here we were using DVR and here we were using DStatCom. So active active example is UPQC that we have been discussing so far. Now, when we talk about the application of passive power filter, so these filters are present in HVDC systems because they are simple, low cost, robust. So again, like the thing we have been discussing so far, the only reason still people are using passive filters is because they are cheap. Other than that, there is no advantage. They are fixed compensation. They, if they are not used to the full load condition, then they cause separate problems in the system. Resonance problems are there. A lot of issues are there with them. But the only reason still people are using it because of its cost effectiveness. And they are extensively used in hybrid configuration. So whenever, in order to, hybrid configuration also became popular because now we know that we have a need for active compensation. But in order to do some cost prevention there, what we do is, we, in order to save some money there, we design a low rating active compensator, and the rest is compensated by passive filters. So these combinations, hybrid configuration is very extensively used. So there is one big problem with passive filters, and that is the problem of resonance. What is resonance? Resonance occurs when my system, uh, all the inductive power that is present is compensated by all the capacitive reactive power. When both of these reactive powers become equal, they cancel out each other, leaving out only the resistive element in the circuit. Basically, you can imagine an RLC circuit in which all the reactive power that inductor needs is supplied by the capacitor. So when this is happening, this RLC circuit is acting like a simple R circuit, right? The equivalent of the circuit could be, if all the reactive power that my inductor needs is supplied by my capacitor, then this circuit will start looking like an equivalent resistive circuit. And because there is no impedance offered by these elements, the impedance reduces. As a result of that, the current which is flowing through that branch increases to a very high limit. And because of this increase in current, our system might trip and we may face a lot of problems. So that is why this resonance is a problem for us. Okay. So passive filters become very sensitive to parallel resonance because of the presence of filter capacitors and source impedance. So the inductor and capacitor in our traditional power system is, we have been discussing the source impedance, right, ZS, and then we have been putting the filter capacitor. So we have been looking at two-leg converters, three-leg converters with the voltage fed type loads, right? This is the most common type of load. That voltage fed type load means loads which have capacitor on the output side. So where we have inductive source impedance, and then we have these capacitors at the output. So when we switch them, there is a time when this kind of circuit comes into picture. And this is a simple LC circuit. So when these circuits behave together, cause resonance, then our circuit might consume a lot of heavy current. So we have to avoid these kind of currents. And therefore, using these passive compensators, this C filter is again a one type of passive filter, right? Just a C. So there are a lot of problems we have to tackle while before implementing this kind of filters. So in parallel resonance, frequency occurs at or near the harmonic produced by the load. A severe voltage distortion or harmonic current amplification may be produced because of the reduction in impedance. Because my net impedance is now reduced only to resistive impedance, therefore my current is increasing. And this may result into blowing of the fuse or break, or overloading of the system. Therefore, we need to take care about this resonance problem when we are designing the system. So at that very moment, we'll have to take care. Otherwise, so we need to analyze the system, find the resonance frequency of the system, and figure out if this resonance frequency is matching with my filter frequency. So we'll take care of these things in the design part. Now, the passive power filter technology is state of the art if we talk about. Currently, passive filters are also used to eliminate voltage harmonics, regulate terminal voltage, suppress voltage flicker, improve voltage balance in the three-phase system. And when we talk about the classification, then they are classified. The classification varies from tuned and damped, then based on the connection, whether they are connected in series or parallel. And then another classification is based on the supply system. Again, two wire, three wire, and four wire. Shunt passive filters have been considered more appropriate to mitigate harmonic currents. We know that the major dominant power quality problem is current and harmonics in the current. So the most important area of application of these passive filters is in shunt for harmonic compensation of currents and partially to meet the reactive power requirement of these loads. That means for power factor correction to relieve the AC network from the problem, especially current fed type of nonlinear loads. So these are for current fed type of loads, and for voltage fed type of loads, series type of filters are considered better. These are just few examples of power filters. Again, we have seen capacitor filters, capacitor banks before, right? These are inductor banks. So these are again AC capacitor banks. So if you look at the classification, classification is based on the topologies or the type of connection or the number of phases. So when we talk about passive power filters, they can be categorized into shunt, series, and hybrid. Now, when we talk about shunt category, then they might either be band pass or tuned, or they might be high pass or damped. Then, so what is the meaning of band pass or tuned? So, suppose I know that my system is having only third harmonic content. Then I will make a filter that is filtering only the third harmonic content. So that is called a tuned filter because I am tuning the frequency of this filter to third harmonic so that it takes care of third harmonic component only. So that is those filters are called tuned filters. But there is another case in which I know that there is third, fifth, seventh, ninth, 11th, all the higher order filters are there, odd ones. If I get this kind of system, will I be putting compensator for each and every one of these frequency components? No, right? It will be very expensive. So I would instead just put a high pass filter there, right? So I tune this high pass filter such that its cutoff frequency is less than third harmonic frequency and greater than fundamental frequency. And then all these harmonics will be taken care of. So this is what we will do for, so this is called high pass or damped filter. So that is the category. So depending on application, what are the harmonics present in your load current, you decide which one to go for. Then when you're tuning, you could either go for a single tuned or a double tuned. Double tuned, single tuned means if in an application, if I'm targeting just the third harmonic, then it will be called single tuned. But if I am in my application, there is third and fifth harmonic, then I will be tuning for both of them. So it will be called double tune. Then it might be triple tune or multi tuned. So depending on whichever is cost effective, the multi tuned one or the high pass or damped one, you figure out which one to go for. So high pass or damped one is categorized into first order, second order, third order, or C type. So the order of these, the first order means there will be one kind of energy, only one energy storing element present. Hence, it's called the first order. In second order, there will be two energy storing elements present, and so on. Okay. Then in series, so when you're talking about shunt connection, then you have to shunt. The purpose of connecting filter in shunt is to pass the high frequency component. So either you use band pass or high pass. But when I'm connecting my filter in series, then I'm connecting this filter in series in order to block, right? Whether I'll block a particular frequency like a tuned, or I will block all the high order frequencies beyond third harmonic. So this is the purpose of my series compensator. And then the third category is hybrid, right? So hybrid of shunt and series or hybrid of tuned and damped filters. So any particular combination of these filters can be can come in the category of hybrid filters. Okay. So these are the examples of shunt, passive tuned, or band pass filters. So you could use any topology. The and how will you distinguish that which category will these belong to? Will be based on their frequency response curves. So suppose my filter has this kind of frequency response curve. That means this is tuned only for one frequency. So I will call it as single tuned. If my filter has this, then this is responsive for two frequencies. So I will call it as double tuned. So based on the frequency response, we decide the category to which these filters belong. Okay. So shunt passive tuned filters can be single, double, triple tuned with series capacitor or triple tuned with series inductor. So depending on the application, you decide which kind of inductor you want. Then in series you have to stop. So you use stop filters, band stop filters there. So you could either stop a particular frequency or multiple frequencies, whichever you want. Then we shunt passive damped or high pass filters. So they are first order, second order, third order, and C type filters. So one energy storing element, two energy storing element second order, three energy storing element third order, and then this is called C type because this part is used for tuning a particular high frequency. But when this part is not working, then for all the higher frequency components, this RC circuit will always, this branch will always be active, this RC branch. Therefore, it is called C type of filter. This is a generic branch for all high frequency components, and this branch is specific for some kind of dominant harmonic. So this is our system. This is my source. This is my load. Then the passive power filter or shunt filter are connected at the point of common coupling of this source and load. Near to the load we try to connect it. Okay. So there might be parallel passive filter or series filters. So if I have fifth and seventh harmonic and other higher order harmonics to be taken care, I'll have one branch for compensating for fifth harmonic, another branch for compensating for seventh harmonic, and then one more branch for compensating rest of all the higher order harmonics. Okay. And then there is hybrid. So hybrid is a combination again. So a lot of combinations can come in this category. Double tuned, triple tuned. Okay. And we call it damped because of the presence of resistive element in these filters. Now, based on the connections, we know that if you look at the overall dynamic topology, then if the filter is connected in series or shunt or both series and shunt, then we can call it as we can have this kind of classification. Yeah, so these were the response curves that we were discussing, right? So this impedance curve shows us that this is a band pass filter and this is a high pass filter because it is passing all the high frequency components. Then this is a double band pass filter. Then this is passing double frequencies and then it is also acting as a high pass filter. This is a composite. Composite basically means combination of lot of variants. Okay. So depending on these curves, impedance versus omega curves, and or there are other frequency curves as well. So depending on these curves, you decide what this filter is doing. Okay. The topology of these filters is not fixed, but you can obtain the response curve and then from there you can tell which kind of filter it is. Okay. So if you want to design a shunt filter for fifth, seventh, and 11th and 13th harmonic, then it would look something like this. So each branch will take care of each harmonic. And for the rest of the harmonics, that branch will just act as high impedance branch as if it is not existing. Then for the category for shunt filters are classified into notch type of filter or double tuned filter or high pass filters. So notch filter means this is notch filter. That means this filter will allow only one particular frequency component. So suppose this is fundamental frequency, first order. So this will be called as a notch filter because it is allowing only the fundamental frequency component. Then double tuned band pass filter means it will allow two frequencies to pass. Let me say that I want first order and third harmonic. So I will tune my filter for first and third harmonic. Then there is high pass filters, also known as damped filters. High pass filter will allow all the frequencies beyond certain levels. Suppose I want all the harmonics to pass which are greater than fifth harmonic. So I will tune my high pass filter in such a way that this is around fifth harmonic. So all the frequency component higher than fifth harmonic will be passed. Now, let us talk about series filters. The series filter, as I know, as we have just discussed, that shunt filters are responsible for passing the bad part through them, and series filter is responsible for blocking the bad part. So, in order to block the bad part, they are designed in such a way that they tackle a particular harmonic. So, if I want for a third harmonic, I can put just one of this branch. If I want for fifth harmonic, I will have to put two of these branches in series in my system. Okay. Then hybrid is again a combination of both series and parallel. And there are multiple topologies of this hybrid filter as well. So you could either have series first and shunt later, or you could have shunt first and series later, or you could have a T type of connection with two series and one shunt, or you could have a pi type of connection with two shunt and one series. There are a lot of possibilities that are present. Okay. Now supply based classification of passive power filters. So based on the supply, the filter could be a single phase filter or a three phase three wire filter or a three phase four wire filter. So the filter could be classified in the category of shunt, series, and hybrid. Okay. So if you look at two-wire passive power filters, so these are the three series filters. This is for third harmonic, for fifth harmonic, and for higher order, high pass series filter. Okay, so these are series filters, and this one is single phase passive shunt filter. Okay, all components are connected in shunt here. And if we talk about three wire, so this is three wire series filter. All the filters are present in series in all the three branches. Then this is a shunt filter connected in shunt with this. So this is an example of shunt. Again, for four wire, this is an example of series filter. This is an example of four wire shunt filter. Now let us look at the principle of operation of passive power filters. The main purpose of passive shunt filters is to reduce harmonic voltages and currents in AC power system to an acceptable level. So instead of just focusing on the name, try to focus on the application of these filters. Once you know that you are trying to take care of harmonics, it will be much more clear. The basic operating principle of passive shunt harmonic filter is to suck or absorb harmonic current in low impedance path, which can be realized using any RL and C components. Whereas in case of passive series filter, we block the harmonic current entering the AC network by the passive tuned LC circuit, offering high impedance for the harmonic currents. So in shunt circuit, we are trying to provide low impedance path to the high frequency components, whereas in series type of circuit, we are trying to provide high impedance part to the harmonic components. Okay. So the kind of filter is determining what kind of impedance we want, whether we want high impedance or low impedance. Okay. Then passive shunt compensators are connected in parallel to the load, and series filters are connected in series. We know that very well, right? So passive filters are the engineering solution for harmonic reduction within an acceptable limit. So they will only reduce. They cannot eliminate. Why that? Because our system does not always operate at a fixed operating point, right? The operating point keeps on changing with time. So when we are providing fixed kind of solution to a variable kind of problem, it can only reduce to an extent. It cannot completely eliminate. If you want to completely eliminate, you will have to go for active kind of compensation.
Madam, to observe or to blocking to eliminate three are not equal, madam.
So absorb or blocking. So blocking, when you are absorbing the harmonic in shunt, what you are doing is you are providing a path with low impedance, right? Instead of looking, okay, let observe this. So suppose I have the shunt compensator, okay, and this is my supply current, and this is having third harmonic component plus fundamental component. Now I want fundamental component to flow through my load, and I want my third harmonic component to flow through my filter. Okay. So when I'm designing this filter, let me say the impedance of this filter is Z3. So I will design Z3 in such a way that it will offer low impedance to the third harmonic component, right? So when I am offering low impedance, that means I3 will be high, right? That means all the third harmonic component will flow through my filter. Why? Because I am designing it in such a way that it offers low impedance. So what I will say in this case is, because of this shunt filter, my shunt filter is absorbing the third harmonic component, right? Now, suppose I put this in series and this is my load. Okay. Again, this is fundamental and third harmonic, and this is my series filter now. And I want only fundamental component to go there. Now, I will design my series filter in such a way that it offers high impedance to third harmonic content, so that only fundamental current is passed. Third harmonic current does not go through it, or it
Means
goes through.
that will stores that series filters or shunt filter stores that energy, madam, remaining energy except fundamental.
They actually have another path inside them where the third harmonic components keep on rotating. That is what actually happens there. So, but the main difference is that when we design shunt compensators, we design it in such a way that this offers low impedance. That is why we call it absorbing the frequencies. Whereas the series filter is blocking the third harmonic component by offering high impedance. So this is the difference between the two. Okay, here it is blocking, here the series filter is blocking, and here the shunt filter is absorbing. So they are not actually the same.
Means what about this I3 component will reflect on the supply or it will be stores in the filter, madam? I have some clarity, madam. This I3 component means this is also having some energy, madam.
Okay, sorry, this should be like this. My load wants both I1 plus I3, and my source will be given only I1. It is actually preventing the source side from sourcing this third harmonic component. The load will still need it, and this third harmonic component will be supplied by this series filter. There will be a capacitor branch which will source this reactive power current.
Okay, okay.
Okay. So in case of passive shunt filters, harmonic voltages are required at the point of common coupling to flow the complete harmonic current to the passive series RLC circuit of the shunt filter. So when we talk about the location, the passive filters are located very close to the loads. Okay, we have to take care of this so that they compensate for the problem there itself, and the source does not have to give any kind of bad current. So now we now talk about the connection. Based on the connection, we have shunt, series, and hybrid configurations, right? So if we talk about the shunt filter, so first of all, the shunt filters are tuned at slightly low frequency at which they want the harmonics to be compensated for. Suppose I want to take care of a fifth order harmonic. Then instead of designing my system directly for fifth order harmonic, what we actually do in practical conditions is we design for 4.7th harmonic or any other harmonic which is less than 5. There are two reasons of doing these things. The first reason is the first reason is that when these components age with time, their value reduces, and then these 4.7th harmonic will automatically shift to fifth harmonic with aging. Okay, so therefore we start with a low one. And the second reason of doing this is when we have fifth harmonic, and we were discussing about resonance problem, right? So during resonance, what happens is net impedance becomes equal to the resistive impedance, and very high currents are drawn from the source system, which is very dangerous. So in order to limit that current, what we do is instead of tuning at exactly the fifth order, we tune it at slightly different from the fifth order, so that we have slight impedance in the circuit which will limit the current. So for current limiting thing, we are doing this. Okay, so in our practical conditions, instead of designing for that particular harmonic, we design at a slightly lower harmonic order. Okay, and if my system has multiple harmonics, then we could go for any multi-tuned filters. And because of the presence of, we have seen that there are both R, L, and C elements. And because of the presence of these R and C elements, what is happening is when R is present, you know that there is losses involved. So because of this involvement of losses, there are harmonic currents in these losses and certain heating takes place. So when we talk about series filters, then passive series filters are tuned at slightly low frequency at which they have to block the harmonic. So again, the same principle that we had just seen for shunt also applies to series filters. And for reducing the number of series connected parallel tune LC filters of passive elements, a high block filter is used in series. So suppose I have a system in which third, fifth, and all the higher order harmonics are present, then I will put one filter for third harmonic, one for fifth, and one high pass filter I will put. Instead of putting, for seventh, 11th, and 13 separately, I just put one high pass filter. That will take care of all the higher order harmonics. Now, the advantage of hybrid configuration is that it takes care of both the series filter, both the drawback of series filter and the drawback of shunt filter. Therefore, hybrid filters are one of the most efficient filters that are used in the category of passive power filters. Now, when we have been discussing about tuning, right? So, how do you know whether you are tuning it to a right frequency and up to what extent, whether your tuning is perfect or your tuning is slightly blurry? How do you decide that? So we all have studied a term called quality factor, right? So quality factor we measure the quality factor in order to know the sharpness of tuning. So you might tune my system in this way, or you might tune the same system in this way. So this is much sharp tuning, right? So these and these shapes depends on the Q factor. Okay. So based on the value of Q, you fix which type of tuning you need. Whether you need a very tight kind of tuning or you need a broad kind of tuning. So based on the application, you fix the value of Q accordingly. So a passive shunt filter is considered to be tuned corresponding to a frequency at which its inductive reactance is equal to its capacitive reactance, right? And for passive shunt filters, which are tuned at lower frequencies, so the Q value for passive shunt filters is in the range of 10 to 100. Okay. Whereas for the passive shunt filters known as damped filters or high pass filters, the Q value lies between 0.5 to 5. And the cost of, if in a system, if the reason why passive filters are very popular is if in an application the cost of filter is in the range of 15 to 20% of the total cost of the system, then they are very much efficient. Then people will definitely go for these. In case the cost reaches to around 50%, then people might not use them. So you have to do the cost analysis based on the rating of your passive filter. Then only you go for the passive filters. So when we talk about the analysis and design of the passive filters, so the procedure as we discussed in the start. So what we do first is we look at the system and we record the input current frequency spectrum of the nonlinear load. Frequency spectrum means basically the thing which we obtain after doing the FFT. Frequency spectrum means a study of what all frequencies are present in that current waveform. That is called frequency spectrum. So we do that analysis of the input current. Then we obtain the frequency response of the power distribution equivalent impedances. That is mod Z versus omega curve, right? Where the passive filter is to be connected in the system. Then we select the numbers and the types of tuned frequencies of the passive filters and which type of filter are we going to use. Whether we are going to use a tuned filter or a first order, second order, or C type filter. So those kind of decisions we take based on these frequency response curves. Then we appropriately assign the reactive power distribution to be generated. So if I am designing three branches, then what will be the share of each of that branch? Whether I am going to give equal distribution of reactive power to all the three branches, or I want to give the 50% of the weightage to only one branch. That decisions we have to take. And after that, based on the reactive power assignment, we find the estimate of the parameters of each unit. What will be the L value, C value, R value all these things. Then we evaluate the attenuation factor for each unit of passive filter as a function of frequency. Then we check the existence of resonant frequencies of each unit. So this is the place where design is complete. Now I am validating that design for the problem of resonance. I check what is the resonance frequency of my system. And if my system has a harmonic which is coinciding with the resonant frequency, that I will check. And if that is a problem, then I'll keep on repeating the steps again and again. Okay. Now, if we look at the design of passive shunt filters, what we'll do is, if in a single phase, there is third and fifth harmonic. When we talk about three phase, third harmonic is gone. It's fifth, seventh, and other odd harmonics. So let us assume that there is the reactive power requirement of the load is QC. Then, in order to find the value of capacitance, we know that QC reactive power is equals to Vs square by Xc. Xc is the capacitive reactance, which is equals to 1 by omega C. So n is the order of frequency that we are targeting. Here it is used m. You could use n or m, anything, doesn't matter. So the value of capacitance is Qc by n omega Vs square. Suppose I want to take care of third order harmonic. So I will place n as 3, omega is 2 pi 50, Vs is whatever is the 230 volt, 260 or 230 or 240 volt, whatever is given in the question, and Qc will be the reactive power requirement of my load. Then we know that the resonance frequency or the system frequency is given by omega is equals to 1 by under root LC for an LC filter, right? So if I want to tune this filter in order to compensate for nth harmonic current, then n omega will be equal to 1 by root LC. So I'll just put n omega here, and then I already just found Cn. So based on this equation, I can find the value of Ln. And using the quality factor in order to find the attenuation, what kind of sharpness I want. Based on that decision, I'll be able to find the value of R resistance. So we just discussed that the value of quality factor or Q is normally in the range of 10 to 100, and for high pass filters it is in the range of 0.5 to 5. So when we talk about the modeling simulation, so these are few examples of the circuits. This is a simple three-phase diode rectifier which are connected using series filters for compensating fifth, seventh, and high pass filters, right? So if you do certain design, then you will observe this kind of waveform. So since this was a series kind of power filter, so if you'll observe that the series power filter has resulted into beautiful sinusoidal supply current. It has blocked all the harmonic components. If you look and since it's connected in series, there is still certain harmonics present in the load voltage. And similarly, you can find the THDs of different supply current, source voltage, and load voltage. Okay, so this way you can do the analysis of these circuits. And there is this circuit with shunt filters. Then there are other topologies with both the combination of both shunt and series filters. So this could be with a transformer. So when you are considering transformer into account, then while drawing the equivalent circuit, you will have to take care of the transformer impedances as well when transformer is involved. Okay, so now if we talk about the limitations of these passive filters are not adaptable to varying system conditions. As we have been discussing so far, that the passive filters provide fixed kind of compensation. They cannot vary the compensation. So because of that problem, this is one of the major limitation, that they provide only fixed kind of compensation to our system. And the change in operating condition of the system may result in detuning of the filter, right? So when operating conditions change, the harmonics that I am getting might change, and therefore the tuning might not be proper. And the design of the passive filter is reasonably affected by the design of source impedance. So if I am able to effectively estimate the source impedance of my system, then it is good. But if I am not able to do that, then it will be a problem, because we have huge electrical network and it's difficult to accurately measure the source impedance in real time scenarios. Then another problem is because of the presence of fixed compensation, the size of the filter might be very high. They are not energy density is not that good for passive filters. And in case, so when we design these filters, we normally design them for full load condition. But what happens is when my system is not operating at the full load condition, then eventually I am providing overcompensation to my system. So in that case, when the filter gets connected, then my point of common coupling voltage increases, and if I take my filter out, then my point of common coupling voltage decreases. So because of that overcompensation problem, the whole purpose of putting this filter was to take care of power quality problem, right? Harmonics. But it itself is giving other power quality problems of voltage distortion, which is not good, which is not at all what we want, right? These are few of the drawbacks of these kind of systems. Then another one is these filters are designed with large number of elements, right? We have seen so many elements, if for separately for third harmonic, for fifth harmonic, seventh harmonic, then high pass filter. So many elements we are putting. So when these passive elements are present in the system or the circuit, they have their own individual losses, right? And then they might lead to resonance, which have very high current, which means very high I square R losses. So these losses have to be taken into picture. Then parallel resonance problem might occur, which might need to, additional power quality problems. When resonance occurs, then there might be different kind of non-characteristics or characteristic harmonics present in the system. And due to the heavy current, my breaker or protection circuit might get damaged. There might be a lot of other problems. Then again, the sizing of these filters is very high. And then the environmental effects such as aging, deterioration, temperature change due to the filters in random manner. So right when we are installing these filters, we predict a kind of working, but with time, age, temperature change, weather change, all these conditions, the working of this filter and parameters will change. Then in some cases there is small DC current present in the distribution system, and these presence of DC component or even harmonics, they may result into the saturation of reactors. Again, when the reactor will saturate, heavy currents will be drawn, right? Special switching is required in switching in and switching out of passive filters to avoid switching transients. So while connecting switching transients, it's like it's equivalent to connecting or disconnecting a load, right? So when I am doing that, I'll have to take special care at what point of my voltage curve I am connecting. So I'll try to make the connection at this point when the voltage is very low in order to avoid the switching transients. Then if there is ground wire present, if in three-phase four-wire circuits are present, then there will be grounded neutral present. And because of the presence of that grounded neutral, there might be amplification of the third harmonic current in some cases. And then in certain cases, in order to monitor the current through the passive filters, you might need special protection equipments or monitoring equipments as well. So it's like additional cost in that case. Okay. So we have discussed the parallel resonance problem in these filters. Now there are ways to mitigate those problems. Why resonance occurs? Because of this source inductor and this filter capacitor. Because of the presence of these equipment, our this parallel resonance is occurring in the system. Now, if we have the mathematical analysis done of the system, then we find one solution to this system where we put an inductor in series with this capacitor. And when we again do the mathematical analysis, then we will observe that using the variable LF filter that we had just put here, using that filter, we can change the resonance frequency of our system according to our need. Initially, it was system dependent, but now using the filter LF, we are able to change that resonance frequency, and we'll make sure that this resonance frequency does not coincide with the harmonic any of the harmonic components of my load current. Okay. Now, the voltage distortion and harmonic currents flowing into the supply system can be computed as follows. So it's like basic simple uh, K- KCL. It's simple KCL. Okay. So current distribution, current divider network, right? So if I have two current components, the harmonic current is divided into both filter and the supply. So it's like just parallel branching. So using the impedance values, you could find these currents. You will be able to clearly understand it in the numericals that we are going to solve. Okay. So then we have been discussing all the. So these are just the. This was just some calculations in order to uh, explain the problem of parallel resonance and its solution. So you can try this out. It's pretty simple calculations. Okay. So these ones are not of that much importance. The main important features are the designing of these filter finding the value of these filter components, how to find those. Okay, and then how to find the rating of our passive compensator. Okay, passive power filters. What will be the power rating, active power rating? What will be the reactive power rating? What will be the VA rating of my compensator? All these questions will be answered in the numericals that we'll be looking up. Okay, so shall we move on to the numerical part of today's lecture? Any doubts so far?
Madam, our transfer system also having a capacitance, madam.
Oh, yes.
Means they will not meet any not using any compensating purpose, madam.
No, both
It
of
will
both the distribution and transmission sector have compensators.
means it will be not designed by it is not man-made, madam. It is automatical formed forming capacitance in between the line to neutral, madam. That is the new use of for that one, madam.
No, so in HVDC networks, as I mentioned, so HVDC comes in the category of like transmission network, right? So there, so depending on requirement, so naturally there is a capacitance which is formed, inter-wire capacitance you're talking about, right?
Yes, madam.
So that is there, but apart from that, at the load end, since the nature of load that we are connecting is mainly lagging in nature, so at the load end we need to provide additional capacitors so that they take care of the reactive power requirement when there are motors connected. So motors draw lagging current. So in order to compensate for that, we put capacitors. So basically, any kind of active compensator is also a capacitor or an inductor. Basically, it's just one is varying and the other one is fixed. But we do need capacitor also, even though they are present in the transmission line. Because during transmission it is fine that capacitor interwinding capacitance and parasitic capacitance are there to take care of my system, but what happens at the load end is that this capacitance, the reactive power that these capacitors are providing is much less than what my system actually needs. That is why I have to put more capacitors there.
Okay, madam.
Okay, okay, so we'll start with the problem solution for today. So today I have taken two main problems. So one will be single phase, another one will be three phase. So we'll just practice the design of these filters and do the analysis of these filters in such a way that they will help you with the assignment problems as well. Okay, so let us start with our first problem for today. Yeah. So in the first problem, a single phase four branch shunt passive filter for compensation of third, fifth, seventh, and high pass filter is used in a single phase 220-volt 50 Hz system to reduce the THD of supply current and to improve the displacement factor to unity. It has a load of thyristor bridge converter operating at 60-degree firing angle, drawing a constant 25 ampere DC current. Let the supply have 5% source impedance, mainly inductive in nature, and calculate the value of elements of the passive filter. Okay, so let us first draw and imagine what kind of circuit this is. So since it's a single phase supply, let me say this is voltage, this is some impedance ZS, which is taking current IS. And there is one branch which is L3 and C3, sorry, it is LC filter, right? Then another branch is L5, C5. Another one is L7, C7. And the last is the high pass filter. Let me call as CH, RH, and LH. So the difference in this high pass filter is only that it has this additional branch this additional branch for all high pass components. Okay. Other than that, it is again the LHCH circuit, a simple LC circuit. Now there is a diode, there is a thyristor type of bridge rectifier, single phase again, and the firing angle of the system is 60 degrees. And the constant DC current that this thyristor is drawing is 25 amperes. Let me say this is my load current that my system is drawing. Let me call it as IDC, and the voltage across load as VDC. And let me say this is my IL, that is a load current. Okay. Now we know that there are 4 branches of our passive filter, and each branch has to take care of each harmonic. Okay. So now the first question is we have to find the value of these elements. So in order to find the value of these elements, the first thing I need to do is find the reactive power consumption of my load, right? In order to find the reactive power compensation consumption of my load, first I know that in this thyristor type of circuit we have already seen, right, in previous classes, that the RMS value of this current is RMS value of load current in such cases is equal to IDC itself, which is equals to 25 amperes. Let me call the RMS value of this load current as IL. Okay. Now we have also seen the Fourier series expansion of these kind of circuits, thyristor bridges, and fundamental RMS current can be found from the same expression. Fundamental RMS input current will be equal to, let me say that is let me say it, call it as IL1. IL1, which is equals to root 2 by pi into IL. So if you have any doubts regarding these derivations, you can look up our previous lecture. We have already done these derivations. This is 22.5 amperes. This is the RMS value of the load current is 25 amperes, and the RMS value of the fundamental component is 22.5 amperes. Now, in order to calculate the
Madam, this
active,
is, I think, madam, this is
sorry,
IS1, madam. This is IS1, madam.
yeah,
You have
IS1 will be
written
equal to
IL1.
this is IL1 because we are talking about the load right now. Only
They
this
written
part,
fundamental RMS of input current, madam.
input load current.
Okay, okay.
It's written load current. Okay. So we are talking about the load right now. Okay. Because active power and reactive power requirement of load we are trying to calculate. Now we know that we have calculated the AC RMS value of the load current and the fundamental component. Now from the fundamental component we know that fundamental active power component of load current is, let me call it as IL1A will be equal to, we know that it is IL1 cos theta, and IL1 cos theta is 22.5 into cos of 60 degrees, which will come out to be 11.25 amperes, right? Now using that we can find fundamental active power. That is P1 will be equal to Vs1 into IL1A or Vs1 IL1 into cos theta. So this will be equal to 220 into IL1 cos theta is 11.25. This will come out to be 2475 watts. Similarly, we can find fundamental reactive power component. That will be, let us call it as Q1. Vs1 into IL1 into sine theta. So we know that it is 220 into IL1 is 22.5 into sine 60. So this will give me Q1 as 4286.8 watts. This is our Q rating. Now, since we are asked to find the value of the compensator, the filter elements. So what we'll do is we'll start, since we know that we have 4 branches, right? So let me assume that each branch will supply equal reactive power. So what we'll do is, in order to find the value of capacitance, I will divide the total reactive power into 4 parts and then use the same equation in order to find the capacitance value, right? We have discussed Q is equals to Vs square by Xc, and Xc is 1 by omega c, so it's V square into omega c. From there we got this equation, and here instead of putting Q, I am putting Q by 4 because each branch is going to give 1/4 of the reactive power, total reactive power that I want. So 4286.8 by 4 divided by 220 square into omega is 2 pi f, and 2 omega is equals to 2 pi f, that is 50, which will be equal to 314 radians per second. So when you solve this, you will get the value of capacitor as 70.48 microfarads. So this capacitor C will be equal to C3, C5, C7 and CH. All will be equal to 70.48 microfarad. So currently we simplified our calculation by assuming equal distribution. If you want, you can take up distribution in different fashion depending on your application. Okay. Now we have to calculate the L values, right? So in order to calculate the L values, we know that for third harmonic we have seen the equation that omega will is equals to 1 by under root LC. So L3 will be equal to 1 by omega 3 square C3, and where omega 3 will be equal to 3 times 314 radian per second, right? So L3 will be equal to 1 by 3 into 314 square into C3, which is equals to 70.48 into 10 to the power minus 6 because it's microfarad. So L3 will come out to be some around 15.98 millihenry. We can call it as 16 millihenry. Similarly, R3 we will find out using the quality factor. Let us assume Q3 to be equal to approximately 50. So for all the circuits, we will assume Q to be 50, and for high pass filter, we can assume to be approximately 2. Okay. So X3 is equals to omega L3. So omega L3 into X, omega into L. So omega is 3 into 314 and L3 16 millihenry by Q we are taking as 50. So this will give us 0.301 ohms. So this is our R3. Now similarly, we can find out the fifth harmonic component, which is again L5 will be equal to omega 5 square into C5, which will be equal to 5 times 314 square. C5 is again same as C3, which is 70.48 microfarad. This will come out to be approximately 5.8 millihenry. Similarly, R5 will be equal to X5 by Q5. So this will come out to be 0.1806 ohms. Similarly, for seventh harmonic component, R7 will be equal to X7 by Q7. Q7 is again 50. 6.37 by 50. This will come out to be 0.129 ohms. Now the last filter, which is high pass filter. So QH for this high pass filter will be taken as 2. Okay. Now, since in the further questions we have been asked to calculate the total harmonic distortion of supply current. So we know that, write it there only. So we know that total harmonic distortion of IS is equals to IS3 square plus IS5 square plus IS7 square plus ISH square under root by IS1A, which is the which is the active part of the current. So this is the THD definition. So I need to find all these parameters first. Okay. And then again in the next part we have been
Madam,
asked.
here, madam, madam,
Yes, yes, sir.
madam, here we have to write square root of IS1 square minus IS square by IS1. That is not total harmonic distortion.
So total harmonic distortion, you can either, subtract what. So we need to have the distortions, right? The problems. So the third harmonic fundamental, either you can subtract if you have RMS, total RMS value minus fundamental, or you can do this. Both will give you the same
Uh,
result, right?
Divided by IS1.
Yeah.
Both are same, madam.
Yeah, yeah, both will give you same results. Then the next part is calculation of total harmonic distortion of the terminal voltage at the load end. So in order to calculate this, we'll need is terminal voltage means VL, that is the load voltage, which is the product of this order harmonic current into source impedance corresponding to that third harmonic. This is the drop. So we'll square this drop. And similarly for the fifth harmonic. Then for the seventh harmonic, so we need to calculate all these things. Then the last one is for the H filter. Okay. So in order to find these parameters, I'll write it right here. Okay. So for the first, so in the first place, the source impedance of the circuit is given as 5%, right? It is equal to ZS, which is equal to JXS. It is given as 5%, J times 0.05 into VRMS by IRMS. VRMS by IRMS. So this is J 0.44 ohms. So this is corresponding to fundamental component. Z is 1. Okay. Now the voltage drop corresponding to the source impedance is VZS, which is equals to J times IL1A into XS. Okay. So IL1A was 11.25 into XS is 0.44. So this will be J times. So this will be equal to J 4.95 volts. Now using both of them, we could find the fundamental voltage across the load. So since they both are 90-degree phase shifted, we can find it using this. We cannot directly subtract them because they both are at 90 degrees. So using Pythagoras theorem, we can find them as 220 square minus 4.95 square, which will come out to be approximately 220 volts. Okay. Now we have calculated L and C values, and then based on those L and C values we can find the source current corresponding to the third harmonic, right? How will we find that? So it's a again current divider rule into Zp3 by Zp3 plus Zs3. So we know that IL3, this equation that we used in order to calculate IL1, this equation. So when we derived it for the general nth harmonic component ILn, it was equals to 2 root 2 by n pi into IL, right? So this n is, it can be written as IL1 by n. So depending on what n is, you can just divide the IL1 by that. That is divided 22.5 by whatever harmonic current you want. So if I want to calculate IL3, I can write it at IL1 by 3. And IL1 is 22.5. Okay, and yeah, Zp3 is during the cancellation while the active components will be working, it will be R3 by R3 plus JXS. Now XS was, we just calculate XS, right? It is this J 0.44, but this was corresponding to fundamental frequency component. But since I am talking about third harmonic component, the omega will be into 3. Okay, so this will be 3 into 0.44. Okay, R3 we had calculated before, right? So this is our R3, 0.301. So IL1 was 22.5 by 3. R3 is 0.301. And since it is J, so we will do the square sum of this and 3 into 0.44 square. So this thing will come out to be, IS3 will come out to be 1.667 amperes. And similarly, third harmonic voltage at point of common coupling will be,
Madam, like this IS1, what about IS1, madam? You calculating IS3. What about IS1, madam?
IS1 we just calculated, right? IS1 is equals to IL1 with just load. So what we are doing is, when we are considering the situation when this compensator will not be there. In that case, IS will be equal to IL, right?
Okay, madam. IS is equal to IL.
Yeah, we are considering the situation in which this filter is not there. Now, when this filter is not there, what are the harmonic components of IS? And from that, we are calculating the filter component values. We are not doing the analysis of system after putting the compensator. We are doing the analysis of this system before putting the compensator. Okay. So this
Okay.
circuit will be after compensation. Okay. Because all our calculations depends on this load. What kind of harmonics are present in the load. So we don't need anything else. Only the load and the source impedance. That's it. Okay. So we're calculating the third harmonic voltage at point of common coupling, which is IS3 into ZS3. Again, ZS3 is equals to 3 times 0.44. This will come out to be 2.2016 volts. Now similarly, we can calculate IS5. All the calculation IL5 will come here. It will be ZP5. It's power filter. ZPF3A. It is okay. So this is ZPF5. Z power filter 5 plus ZS5. Okay. So IL5 is again IL1 by 5. That by n factor is coming. Okay. R5 by R5 plus J times 5 into 0.44. So R5 we have already calculated. It's 0.11806. So it will be 22.5 by 5 1806 by 0.1806 square plus 5 into 0.44 square root of all of this. So this will come out to be 0.3683 amperes. Similarly, you can find this is Vs3. Similarly, you can find Vs5 as Is5 into Zs5. This is the point of common coupling voltage due to fifth harmonic component, which will be equal to 0.3683 into 5 into 0.44, which will come out to be 0.81 volts. Similarly, for seventh harmonic, we can find IS7 as IL7 into ZPF7 by ZPF7 plus JXS7. Yes. So the value of IL7 will be IL1 by 7. ZPF7 is R7 plus JXS7. So IL7 is again 22.5 by 7 and R7 was 0.129. This will come out to be 0.134 amperes and Vs7 will come out to be 0.4144 volts. Now similarly, the last current that we need to find is ISH, which is equals to ILH into ZPFH by ZPFH plus ZSH. Now we need to find ILH for this, and ILH is equals to all the rest of the harmonic current apart from the third, fifth and seventh. So we can calculate it by IL square minus IL1 square minus IL3 square minus IL5 square minus IL7 square, and we have calculated all these components so far, right? So by putting the values, we can get the value of current is 5.649 amperes. So this is ILH. Now we can find ISH as ILH into ZPFH. ZPFH is RH upon RH plus JXSH. So this H will be equal to 9. Why? Because we have taken up to 7th harmonic. Now we want all the harmonic components after the 9th harmonic to be passed through this high pass filter. So therefore we are taking H as equal to 9. Okay. So ILH we already know the value. It's 5.649 into RH. RH value we had calculated before, which is equals to 2.508 by 2.508 square plus this is 9 into 0.44 square. So after solving this, ISH will come out to be 3.0237 amperes. And using that ISH, we can calculate VSH as equals to 11.97 volts. Now we can put all these values that we have been calculating so far, and by putting these values of IS3, IS5, IS7, and ISH and dividing it by IS1A, you will be able to obtain the THD for supply current as, this will come out to be this, and in percentage you can write it as 30.89%. Okay. Similarly, in the next part, we were asked to calculate the terminal voltage. So we again have these components. We have XS3 and IS3 and all these respective components. And if you find the value, then it will come out to be approximately 5.55%. Okay, VS1 is simple, 220 volts. Let us move on to the next part. So the next part is the current rating of the passive filter. So we know that the current rating of, after compensating for all these currents, what all currents are remaining, that will define the current rating of my passive filter. So in order to calculate the current rating of the passive filter, let me call it as IPF. It will be equal to under root of, so load RMS current square minus active part of the load current minus IS3 square minus IS5 square minus IS7 square minus ISH square. After compensating for all those harmonics and the active component, whatever is remaining, that will define the current rating of my passive filter. So this is the current rating. And then based on this current rating, we can find the kVA rating. So the kVA rating of my passive filter will be VPF into IPF. Now this is, since this is a shunt filter, it will be 220. I we just calculated 2.22.054, which will come out to be 4851.9 volt amperes. So this is how we were able to calculate the,
Madam,
yes.
madam, what is the value of supply RMS count after putting the passive filter, madam?
So the
It may
supply,
be
so once we have compensated for these currents, initially without these filters, our supply current was equal to the load current, right? Now my load still requires all these non-linear or the harmonic currents, but these filters will take care of these harmonic currents. So my source will supply only the fundamental active part of the current.
means that is equivalent to fundamental value. That's the only, madam.
Yes, IS1A. That means this I cos theta part. Only that part of the current will be supplied by the source. Rest all these harmonic currents, this branch will give IS3, this will give IS5, this will give IS7, ISH, like this. Okay. Okay, let us move on to our next problem for today. So as a part of the next problem, we are considering a three-phase branch now, a three-phase circuit. So a three-phase, one branch shunt passive filter, which is 11th order high pass damped filter, is employed to reduce the THD of the supply current and to improve the displacement factor to unity of a three-phase 415 volt 50 hertz non-linear load, which is consisting of a 12 pulse thyristor bridge converter with 200 ampere constant DC current at 30-degree firing angle of its thyristors. This converter consists of an ideal transformer with single primary star connected winding and two secondary windings connected in star and delta with same line voltages to provide 30-degree phase shift between two sets of three-phase output voltages. Two pulse thyristor bridges are connected in series to form this 12 pulse AC/DC converter. Let the supply has 5% source impedance, mainly inductive in nature. So first we are asked to calculate the fundamental active power drawn by the load, then fundamental reactive power drawn by the load. then values of the filter elements, then THD of the supply current with filter with passive filter, THD of the load voltage with passive filter, and then at the end the VA rating of the passive filter. So we have performed the same problem with a single phase circuit. The same problem we'll be performing now with a three phase circuit. Okay. So this problem, we have done a variant of this problem before. We connected two 6 pulse converters and phase shifted them by 30 degrees to form a 12 pulse converter. Even in the previous class we did that, right? So let us first draw how the circuit will actually look like. So let us say this is my three phase voltage supply. This is VSA, VSB and VSC. Okay. Now this is primary is connected in star. Now let me say that this is my source impedance. Then there is a filter connected to this system. Let me say this is a high pass damped filter. So this filter will look something like this: a capacitor, inductor and a resistor, same as what we did before. And since our circuit needs to take care of harmonics which are greater than 11 and which are greater than 11th harmonic, so I'll call it as R11, L11 and C11. Okay. Now in the secondary there are two circuits. One is connected using the star connection. This is connected to a thyristor bridge. Then another is connected in delta fashion. Why they are connected in star and delta fashion? In order to provide 30-degree phase shift. And why we need 30-degree phase shift? Because we are using two 6 pulse converters to form a 12 pulse converters. By connecting these two 6 pulse converters which are phase shifted by 30 degree, we are able to obtain a 12 pulse converter. And this is my load which requires the output of a 12 pulse converter. Okay. Now let me call this branch current as IPF, that is I passive filter, and let me call this as I load, and let me call this as I source. Okay. So now we'll start with the first part where we have to calculate the active power, fundamental active power of the load. Now we have discussed that in the previous section that the current consumption of this kind of network is equivalent to stepped waveform which have quarter wave symmetry. That means our waveform looks something like this. Okay. So this is 1/4 of my circuit. So this is say alpha. Then this will be alpha plus pi by 6. And this will be alpha plus pi by 3. And this will be alpha plus pi by 2. And the magnitudes will be IDC by root 3, IDC into 1 plus 1 by root 3, and IDC into 1 plus 2 by root 3. This we have already discussed last time, right? So this is 1/4 of our full wave. Hence, this is called quarter wave symmetry. Okay, so we can just do the analysis of this 1/4 part, and then rest of the thing will replicate itself. Okay, now we have discussed the expressions for RMS current of 12 pulse converter, which is equals to 1.577 times IDC. And IDC is given as in this question as 200 amperes, right? So this will come out to be 315.47 amperes. Okay. Now the fundamental component of 12 pulse converter is given by 2 root 6 by pi into IDC, which is equals to 1.5593 into IDC, which will be equal to 311.879 amperes. This is the fundamental component. Now, active power component of supply current. It will be similar to what we have been doing for the single phase, only this is for three phase, that's it. We'll again IS1 cos theta
Madam, this
1.
is before putting the compensator, after putting the MC, we are getting this value, madam.
Sir, this
Fundamental
is
component.
without the we are just focusing on the load, that's it. If I am talking about the active power consumption by the load, that means it does not care about anything else, just the load. That means just the 12 pulse converter, that's it. So this is our active power component for the fundamental part. Now we need to calculate the reactive power component. So similarly, we can write Q as 3 Vs into IS1 or IL1 into sine theta 1. So this will come out to be 112.089 kVAR. Okay. So this was the behavior of our load without the compensator so far. Only we are focusing only on the load so far, nothing else. Now because of this current, we are given the source impedance as 5%, which is equals to J times 0.05 times Vrms, that is 415 by root 3, and this is Irms, which is 315.47. We had just calculated it. Okay. This will come out to be J 0.038 ohms. This is our source impedance. And drop across source impedance can be found as this is the active part of the supply current IS1A into this is ZS. This will give me 10.257 volts. So this is my voltage drop across the source impedance. Okay. Now using this we can find the load voltage. So fundamental voltage across load will again be Vs square minus Vzs square. So Vs is again 415 by root 3 square minus 10.257 square, which will come out to be approximately 39.6 volts. Now we are asked to find the value of filter elements. So we have only one high pass filter here, right? So in order to calculate, and since this is a three-phase circuit, so there will be three such branches. So I will divide the total reactive power of my system, which is 112089 vars. That was in kVAR, so I'm converting it into vars. This total reactive power will be divided into three parts because there are three branches. Three branches for three-phase circuit. So capacitance value will be equal to Q1 by 3 divided by Vs square into omega, right? So Q1 is 112089 by 3. Vs square is 239.6 square. Omega is 2 pi f, that is 314. So this will come out to be 2071.659 microfarad. So this is the value of capacitor. So CH will be equal to C, which is equals to 2071.659 microfarad, right? Similarly, LH we know it is will be equal to 1 by omega h square into CH, and omega h here will is equal to 11. We have already discussed this, right? So 1 by 11 into 314 square into 2071.659 into 10 to the power 6. This LH will come out to be approximately 0.04 millihenries. Okay, we still have to calculate RH. Okay, I'll write it here. Okay, so RH is equals to again XH by QH, and quality factor we know for high pass filter will be equal to 2, and X we have already found omega into L. So this RH will come out to be 0.07 ohms. Okay, so we have calculated all the filter elements. Now we are asked to calculate the THD or supply current. We know that the THD or supply current is ISH square by IS1A. So we just have to calculate ISH. So ISH is equals to, we know that it's ILH into ZPFH by ZPFH plus ZSH. So ILH is equals to, load harmonic part is equals to IL RMS square minus IL fundamental square. This is equals to 315.47 square minus 311.879 square. This will come out to be approximately 47.46 amperes. Okay, so ISH can be found out as ILH into ZPFH as RH upon RH plus JXH. This will be 47.46 into RH was 0.07 upon 0.07 square plus 11 times 0.038 square, right? So this will come out to be ISH is equals to 7.839 amperes. So using this, we can calculate the THD of IS as 7.839 by IS1A. IS1A was 270.095. 270.095. This will come out to be approximately 2.9%. Now, in the next part, we are asked to calculate the total harmonic distortion of load voltage with passive filter. So we have done this in the previous part also. This will be equal to ISH into XSH square by VS1 into 100. So when you put these respective values that we just calculated, you will get this approximately 1.36%. In the next part, we have to calculate the VA rating of the passive filter. So we know the voltage rating, we just have to calculate the current rating of the passive filter, which is again given by IS square minus IS1A square minus ISH square is equals to, it will come out to be 162.815 amperes. And therefore voltage rating of the passive power filter is VPF into IPF. And since it's three phase, it will be 3 times. 3 times Vs into IPF, which is 3 times 415 by root 3 into 162.815, which will come out to be 117.031 kVA. This is the VA rating of the passive filter. So this is how you will design your passive filter for your circuits. Uh, for either for single phase or three phase, the equations remain the same. Only a factor of 3 came, and just we had to calculate the phase voltage from the line voltage that was given in the question. Apart from that, everything stayed the same. Okay, so you just have to apply the same concepts to all the circuits that you will be getting in the further questions. Okay. I hope you don't have any doubts in the part that we discussed so far.
Madam, for this problem, madam, after putting the filters, the supply RMS value supply current becomes fundamental values, madam.
Yes, it will supply only the I cos phi part because the rest 11th and above all the harmonic is taken care by this filter, high pass damped filter, and
But
it will not.
we have to subtract IS square minus I11 square, madam.
Yes, so the current that we obtained here, you can directly call it as I cos theta, right? The only active part of the current will be supplied, which is this active power component of the supply current. This is IS1 cos theta 1. So only this part will be supplied by the current after the application of the passive filter. But these calculations are valid only for the full load condition. But when my system operating point will change, these values will change. But since you are designing for the full load condition, right now they will be like perfect compensation will be present. But later on in the system, the compensation will not be absolute. Okay. Anybody else has any other doubts?
No, madam.
Okay. Okay, Venkat sir, you can ask that question on the discussion forum that you had doubt. And in case you still want me to discuss that question in the class, you can just mail me the assignment number, question number, and what your exact doubt is. Okay, so I'll take that up in the next class then.
Okay, madam. Madam, one second, you have to give that mail ID, madam. Your mail.
Okay, I'll write my mail ID in the chat box. Just one second, Asif sir. I'll just answer your query. Yes, sir. I have put my mail ID in the chat box. You can take from there. It's ANCHAL. Okay, maybe you are typing it as I. That is why I didn't get any mail from you so far. ANCHALTHAKUR@iisc.ac.in. Okay, without passive filter. So, Asif sir, what we have been doing so far is, so if you look at this circuit, so when I'm talking about the load part, then I am calculating without passive filter only. So what we are doing is, wait. So if I have this system, if this is my source and this is my load, okay. Now my load is drawing non-linear current, okay. Without the compensator, this is my source current and load current are same, okay. And this current is non-linear in nature. Now, when before putting the filter, while designing the filter, what we are doing is we are first calculating this load current. All the load current calculations that we have done in both the numericals today are all the calculations that we have done using both the numericals today have calculated IL. We have looked at the waveform of the load current, and then from that waveform of the load current, we calculated what all harmonic currents are present in this load current. And using those components, then we had designed the filter. So with the filter, IS will only be equal to IS1A, which is IL cos theta component. That is only the active part of the component will be supplied once I have connected the filter. So all the analysis that we have been doing so far is without filter only, because the procedure to calculate the passive filter components is by finding the load current waveform and its harmonic components. So so if you look at the numerical example that we discussed, so let us look at the single phase case. Okay, so in the single phase case, the numerical that we were looking at, so the first thing we did is we found out the RMS value of the load current and the fundamental RMS current. Both of these calculations, sorry, yeah, both of these calculations were done by keeping only this load in mind. This load, that's it. We didn't think about the passive filters at all. All these, because while we are doing the calculation, what I'll do is I will see what kind of harmonic currents are needed by my thyristor bridge. That means I will consider this thyristor bridge only alone, and I will see what IL, what is the waveform of IL, what are the harmonic currents components that are present in IL. So when I am calculating this RMS value and the fundamental value, only this thyristor bridge is concerned. So in the previous tutorial, we have derived the ways of finding the RMS value of the load current of thyristor bridge and fundamental RMS input current of the thyristor bridge. All these things we have seen in the last class. So using those same formulas, we had calculated this 25 amperes and 22.5 amperes. So these values are without the passive filters. Nowhere in the picture I am bringing passive filters. While designing this passive filter, so now what did I do? I calculated the RMS current of RMS load current. Then I calculated the fundamental load current. They are both just with respect to the load. Okay. Then I calculated the active power requirement of the load and the reactive power requirement of the load. So again, I am not talking anything about the passive filter so far. Now, after getting the total reactive power of my load, now I am talking about the filter. Now I am saying that now since I want to design the filter and I am going to take four branches in my circuit, I am going to design my filter in such a way that each branch gives equal amount of reactive power. So that is how I am able to calculate the value of C. Okay. But all the calculations so far is have been done without compensator. It's completely focused on the load. This much up to this cross line, all the calculation have just talked about the load. So from the load I got my reactive power requirement. From that reactive power requirement, now I calculate the value of capacitor in my filters. Now after calculating the value of capacitors, I know that I want these filters to be designed for, say, third harmonic component. So to design this filter for third harmonic component, I calculated L3 by substituting omega as 3 times the fundamental frequency, because I wanted to tune my filter for the third harmonic frequency. So that is how I calculated my L and C values. And for calculating my R3 value, that is just to mark the sharpness of my tuning, whether I want to tune like this or want to tune like this. These sharpness are defined by this R value. Okay, so that is just that. So now after calculating all my components, this IS3, IS5 is the current that is going into my branch. This suppose this is my passive filter branch for third harmonic. So this IS3 is the current that is going in that is coming from this branch. Okay, so that is what is happening here. Okay, so at the end of this calculation, what will happen is after finding all the values, when I will make this circuit, now this whole circuit, if I consider, after putting all these filters with L3, C3, L5, C5, L7, C7, and LH, CH, and RH, after putting all these filters, what will happen is my IS after compensation will become equal to IL. Suppose my initial, the current that my system was drawing was IL. So now after compensation, what is happening is my IS is equals to IL1 cos theta. Only the active part of the current is supplied by the source. No harmonic component is supplied by the source. But initially what was happening is all the harmonic currents were supplied by my source current. All the third harmonic, fifth harmonic, seventh harmonic, and ISH. everything was coming from the source. So I can write here. So before compensation, IS was equals to fundamental current plus third harmonic plus fifth harmonic plus seventh harmonic plus ISH, all the components. But after compensation, what happened? IS is equals to IS1 only. Because all these IS3, IS5, IS7 and ISH are supplied by passive filters. To the thyristor bridge circuit. I hope you got the doubt, Asif sir. If you still have a doubt, you can unmute yourself and ask.
Yeah, madam. I got the answer, madam. This IS1 is equal to IL1 cos theta.
Yes, yes. So, Asif sir, is your doubt clear?
Yes, madam. Clear, madam.
Okay, sir.
Sir, madam.
Then,
Yes, sir.
okay, okay, sir. Okay. Okay, so guys, if you don't have any doubts, then we can end today's session.
Thank you, madam.
Okay, thank you, sir. Good evening.